as we said, the partial derivatives were just the derivative of a curve, right? And how do we obtain that curve? We obtain that curve when I have this surface, and if I slice it with, let's say, the plane y is equal to 3, or as a matter of fact, any constant, right? The intersection is going to be a curve, this curve right here, okay? And if you want to find the derivative of this curve, then we just apply cal1, right? Which means we treat any other variable, in this case, the variable x, because this function depends only on x and y. We treat the x variable as a constant, and the derivative that I'm going to obtain at the point B is nothing else but the slope of this tangent line, okay? Similarly, if I cut this surface with a plane x is equal to a constant, in this case x is equal to 3, I get as an intersection another curve, right? Okay, and then the derivative of this curve at the point B is nothing else but the partial derivative of the function defined in two variables at the point B, right? And we said what we said. When we're looking for the partial derivative with respect to x, we treat all the y values as constant. So that means we're looking for, basically we're boiling down to finding derivative in one variable. And what does this derivative, what does it give us? It gives us the slope of this tangent line, right? The tangent line to the curve obtained by intersecting the surface and the plane. Okay, and of course, Charles asked the question, well, what will happen if I slice this, surface with the plane that it's not perpendicular, sorry, there is not perpendicular to the x-axis nor to the y-axis, okay? There is this plane here, in our particular case, x is equal to y, also goes through the point B, and then we obtain this curve right here, okay? So can we find the derivative of, this curve right at the point B? Well, the answer is yes, and that's called directional derivative. Why? Because we have a particular direction in which we're looking for that derivative. The directional derivative will give us nothing else but the rate of change of the curve at the point B. Okay? So now I'm going to use a graph that it's already there for us in the book, and I will use that one for a little bit. So I'll continue with this. Okay. So here we are, right? I have a surface S, right? That's defined as f of xy, okay? I have a point P of x naught, y naught, z naught, okay? And I'm looking for the derivative at the point P. How did we obtain the point P? We obtained the point P by intersecting the surface S with this plane here, okay? With this plane that makes a particular angle with the positive x-axis, okay? Which means that I'm looking for the derivative in the direction of the unit vector u. Okay. Now, how do we find derivatives? Well, in calculus, what do? We do approximation, right? So, am I going to be able to do this? Let's say that this is a straight line. Sorry about that. Let's say that this is a straight line, and maybe this is not the best color, so I'm going to use, okay, this color, okay? So let's say that this is a straight line. How do we call a line that passes through 2 points on a curve? We call it a secant line, right? So can I find the slope of a secant line? Well, that's easy, right? I can easily find the slope of a secant line. How? Well, that's going to be the values of x and y of q minus the values of x, y, and z of the sorry, the values of z coordinate in q minus the value of the z coordinate in p divided by y minus y naught and x minus x naught. But now the question is, how am I going to send, when I send that, how do I approximate, approach from q to p? Okay, well, I have to look at these two in the dimension x and y. Okay, how is the point p and point q produced? Well, that just we just evaluate p prime and q prime. Okay, p prime and q prime evaluated at a particular function. I got p and q. Okay, so that means that I have to send q prime to p prime somehow. And in order to do that, okay, I have to find the relation with respect to u. Why with respect to u? Because u as a vector, it's a unit vector, but it gives us the direction. Okay, well, that's going to be easy because the vector p prime q prime is what? Is nothing else but h, right? H is going to be some value that after that is going to be sent to 0. As h goes to 0, q prime approaches to p prime, and as q prime goes to p prime, q will approach to p, and eventually we'll get the slope of the tangent line, right? So I need to find the expression for q prime p prime, and that's some constant h times u. Again, u just gives us the direction because it's a unit vector, and that gives us h times a, h times b as components of the vector, where a and b are components of the unit vector. Okay, but now look at this. This here is x naught, so this value is x, and this value here is x naught, right? That means that the x component of the vector p prime q prime, ha, is nothing else but x minus x naught. So x minus x naught is ha. Similarly, y minus y naught is hb, and now I can finally write down the slope of the secant line, which is delta z, change in z, as I said before, change in the z value, right, over h, right? And that's z minus z naught, and z minus z naught evaluated in x and y is this right here, right? Because if you just take x naught and put it on the side of x ha, you get that x is equal to x naught plus ha, and y is y naught plus ha. So this here is the definition of the directional derivative, right? Is the definition of the directional derivative in the direction of u, right? As long as, whoa, as long as we find the derivative, as long as we find the derivative of that ratio. Okay, so just give me a second here. Yeah. So if you find the limit of that ratio, you get what is called the directional derivative of the function f at a given point in the direction of a unit vector u. Okay, and we can use this definition, or simply we can move on to this theorem that says that the directional derivative of f at the point xy is nothing else but partial f partial x times the x component of the unit vector plus partial f partial y times the b component of the unit vector. Okay, so the directional derivative of the function f in the direction of the unit vector u is equal to times x times a plus times b, where the unit vector is defined with components a and b. Okay, it's as easy as that. And now I don't know if did we do an example like this before or not.
I don't think so.
No, we didn't do any examples. Okay, so let's do a simple one, very easy one. Example one. Find the derivative, okay, of f of defined in two variables, x squared plus xy, at the point p naught 1 2 in the direction of the vector v. I feel like we did this one in the direction of the.
We did do this one, I think.
We did this one exactly.
Yeah.
So let's just
in the
do
direction
another.
of root 2.
Yeah. Okay. So
Yeah, we did it.
so let's do another one. How can I change this? Y times x squared plus x times y times e to power y. There you go. Okay. At the point, let's put 0 here because I want to evaluate e to power 0 a little bit easier, right? And then give me two values. Anybody? I don't know. Andrea, give me two constants. Perfect. 1 and negative 2. Okay. Okay. So what do we have to do? Your mic doesn't work. Yeah, it's all good. So the derivative with respect to u of f evaluated at 0.10 is equal to what? The partial derivative with respect to x evaluated at 10 times a plus the partial derivative with respect to y evaluated at 10 times b, where where the unit vector has components a, b, right? Now the unit vector has to be a vector in the direction of v. So the first thing that we want to do is find u, okay? So u is equal to v over its magnitude. So that's 1 negative 2 over the square root of 1 plus negative 2 squared, which is 4, which is 1 over square root of 5, 1 and negative 2. Okay? Or because I'm going to use the components a and b, I can write this as 1 over square root of 5 and negative 2 over square root of 5. Okay? Then partial f, partial x, and partial f, partial y evaluated at 0.10 is equal to derivative of xy squared with respect to x is 2xy plus here both of these are being treated as a constant, y times e to the power of y. Okay, evaluated at the point 1, 0, because both of these are multiplied by y, and I'm evaluating at the point where y is 0, I just get 0, right? 2 times 0 is 0, 0 times 1 is 0. Partial f partial y evaluated at 1, 0 is equal to x squared, right? Because I'm looking for the derivative with respect to y, plus here x is a constant, and for these two I have to use the product rule, y times e to the power y. Okay, so the derivative of y is 1, so e to the power of y, plus y times the derivative of e to the power y, which is e to the power y. Evaluated at 1, 0, well, what do we get? 1 squared is 1, plus 1 times, this guy here is just going to be 0, because 0 times 1 is 0, but this is going to be e to the power 0 is 1, so 1 times 1 is 1, is equal to 2. And finally, if I want to find what is the slope, okay, at the point 1, 0, and then I don't know what are we going to get here. This is going to be 0, 1, 0, 0, right? That belongs to this surface, right? In the direction of the u that we found is just going to be equal to partial f partial x evaluated at this point, which is 0, times 1 over square root of 5, plus 2 partial y, partial f partial y, which is 2, times the y component of the unit vector, which is negative 2 over square root of 5. So you get negative 4 over square root of 5. Of course, as a derivative, as we expect, what do we get? We get a scalar, right? Which just gives you the rate of change of the z value of this function in the direction of the given vector. Any questions? Well, of course, if I want to find the directional derivative with respect to u of a function x, y, right, in the direction of the vector 1, 0, that's this vector right here, right? What am I going to get? I get partial x times 1 plus